Hi all. In this lecture, let us have a brief introduction on backtracking. What is backtracking? Backtracking explores all potential solutions and abandoning those that fail to meet the problem's constraints. So we have to remember two things. One is it explores all possible potential solutions and it will abandon the solution that fails to meet the problem's constraints. It builds candidates for the solution and abandons a candidate as soon as it determines that the candidate cannot possibly lead to a valid solution. The backtracking design paradigm can solve the following types of problems. The first one is enumeration problem, listing all possible valid solutions to a given problem. Decision problem is determining whether at least one valid solution exists or not. It is a kind of yes or no solution. And the third one is optimization problem, finding the best solution according to a specific objective function. Here the objective function could be a maximizing function or a minimizing function while satisfying given constraints. So let us discuss the key concepts that are in backtracking. The first one is state space tree. So in the right hand side, we could see a state space tree. Okay, here one is the root, and 2, 3, 4, and 5 are children. A conceptual tree which where each node represents a partial solution. The root represents an empty solution, and each level represents a decision point adding components to the solution. Here there are two kinds of nodes. One is promising node and the other one is non-promising node. A promising node is a node that can potentially lead to a valid solution, whereas non-promising node is a node that cannot lead to a valid solution and it should be abandoned. Here, in this figure, okay, we have made a cross mark, so which is a non-promising node, okay, and whichever, we have to eliminate the non-promising node. Then the third thing is pruning. The process of eliminating non-promising nodes to reduce the number of solutions to be explored, thereby optimizing the search process. This process is called pruning. The next state is answer state. A state in the state space tree that represents a complete and a valid solution to the problem. If the algorithm reaches an answer state, it either returns a solution or continues searching for more solution if required. And the next one is live node. A node in the state space tree that has been generated but not yet explored is called live node. It is waiting for further expansion, meaning the algorithm has yet to explore its children. These nodes are stored in data structure, usually a stack for DFS, which is a depth first search, or a queue for breadth first search. And the next node is E node, which is an expanding node. A live node that is currently being expanded, that is, the children are being generated. It is called live expanding node. At any given time, there is only one E node, which is the node currently under consideration. Once the E node has been fully explored, the algorithm moves to the next live node. And the next one is a dead node, a node that cannot lead to a solution or has already been fully explored is called a dead node. It is either pruned due to constraints or completely expanded without yielding a valid solution. Dead nodes are discarded to optimize the search process. So this is how searching will happen in a state space tree. Steps involved in searching. The first step is start at the root node. The algorithm starts at the root node, which represents an empty or initial state. It picks the first available decision, moves to the next level. Step 2 is expand the current node, which is E node. The current node, E node, is expanded by generating its child nodes. Step 3, apply feasibility check. A bounding function is applied to determine whether a node is promising, that is capable of leading to a valid solution. Step 4, if the node is promising, continue searching. If the node satisfies the constraints, it becomes a new E node and the algorithm moves deeper into the tree, which is a DFS approach. Step 5, if the node is a non-promising node, backtrack. If a node violates constraints, it is marked as dead node and discarded. The algorithm backtracks to the last valid node and explores an alternative path. Step 6, stop when a solution is found or all paths are explored. If a valid solution is found, it is recorded. If no more paths exist, the algorithm terminates. So this is the general working. Here in the right hand side, it is whatever is given as a state space tree. Here we have marked two nodes. One is a goal node, the other one is a dead node. There are levels: first level decision, second level expansion, and third level expansion. So the figure beside show that the state space tree demonstrates the general working of backtracking. Here X represents the prune node, which is a non-promising node. So this node is a non-promising node, which is a prune node. Here we have to perform pruning. And this goal is a node where the solution is found. This is a general backtracking algorithm. Input node U starts with root of the state space tree, output the result of the problem. So we have to start with if U is a promising node, then U is a goal, then we have to print the solution. Else, for each V where V belongs to child of U, do next we have to try V. Then keep doing it until you explore the solution. So just end the for, end if, and end this if, and end the process itself. So here the general method of backtracking is given. Start with an empty solution, incrementally add components to the solution, check if the current solution is promising, proceed to add more components. If not promising, backtrack. Whenever it is not promising, we have to do backtrack by removing the last added component and try the next alternative. Continue this process until a complete and valid solution is found. All possible solutions have been explored. So here we have some common applications of backtracking. One is n queens problem. We are placing n queens on an n cross n chessboard. Then sum of subsets problem, finding subsets whose sum equals a target. Then next one is graph coloring, assigning colors to graph's vertices. Hamiltonian cycles, finding a cycle visiting all vertices exactly once. So whatever we saw now is just the introduction of backtracking algorithm design paradigm. Thank you for watching this video.